Hello everyone.
Today, we'll be considering two important types of genetic inheritance. First, X-linked, and second, mitochondrial inheritance.
Both of them play crucial roles in how genetic traits and disorders are passed down through generations.
Let's start with the X-linked inheritance. X genes refer to the genes that are located on the X chromosome, one of the sex chromosomes in human.
Females have two X chromosomes, XX, while males have one X and one Y chromosome, XY.
This difference implies that the X-linked traits will have a different manner of inheritance between males and females.
X-linked recessive inheritance, a mutation in a gene on the X chromosome can give rise to a characteristic or disorder.
Males are more commonly affected by X-linked recessive traits because they only have one chromosome.
If a male is affected with a disorder due to a mutation on the X chromosome, because of a lacking matching second X chromosome, it'll be expressed.
For instance, hemophilia and Duchenne muscular dystrophy are X-linked recessive disorders.
If a male inherits the affected X chromosome from its mother, who is a carrier of the disorder, the male child will inherit the disorder.
On the other hand, however, females will have to inherit two copies of the defective gene, one from each parent, in order for them to express the trait.
Otherwise, they may represent carriers and do not show any symptom of the disorder.
In sharp contrast, however, X-linked dominant inheritance is a mode of inheritance in which a single abnormal gene on one of the X chromosomes causes the characteristic or the disorder. When the mother alone is a carrier of the mutated gene, she herself will have the disorder. Her children will inherit the disorder as follows. Daughters and sons 50% will have the disorder, but 50% will be unaffected. Children of either sex have an even chance of receiving either of the mother's two X chromosomes. Let's look at scenario number 1. There's a hemophilia carrier mother. Let's call her Emily. She carries one normal X chromosome called XN and one mutated X chromosome, which we could call XM. And that mutated chromosome XM is responsible for hemophilia. Emily herself is a carrier, meaning that she doesn't exhibit the symptoms of hemophilia, but can pass the mutated gene to her children.
So, her children, what about them? So her daughters will inherit one X chromosome from her, and they have a 50% chance of receiving the normal XN chromosome from Emily, and a 50% chance of receiving the XM chromosome, the mutated one. If they inherit the XM chromosome, they will be carriers just like Emily.
Emily's son inherits the X chromosome from her too. They have a 50% chance of receiving the XN chromosome, which is the normal one, and a 50% chance of receiving the XM chromosome, the one that contains hemophilia. If her son inherits the XM chromosome, then they will have hemophilia.
Emily's children have an equal chance of inheriting either of her two X chromosomes. Daughters may be carriers or they may be unaffected, while sons may have hemophilia or be unaffected. The 50% chance reflects the random assortment of chromosomes during meiosis.
Let's look at a real-life example. Queen Victoria and hemophilia. Queen Victoria of England was a famous carrier of hemophilia. She passed the mutated gene to several of her children, including her son Leopold, who had hemophilia as well. Queen Victoria's daughters were carriers, and some of their descendants, including European royal families, inherited the disorder.
Once again, both males and females could be affected, but the modes of inheritance might be different.
Females are easily affected with X-linked dominant trait compared to X-linked recessive trait, since only one mutant gene is needed for the expression of this disorder.
Mitochondrial inheritance, unlike X-linked inheritance, involves mitochondrial DNA from the mother to the offspring.
Mitochondria are the energy powerhouses. During fertilization, the mitochondria in the sperm are completely destroyed, and the offspring will inherit only the mother's mitochondria.
In other words, mutations in the mitochondrial DNA are transferred from the mother to all her children, irrespective of their sex, though only the daughter will take the mutation to the next generation.
Sons inherit the mitochondrial mutations but cannot pass them on. This is seen in diseases like Leber's hereditary optic neuropathy, otherwise known as LHON, and mitochondrial myopathy.
To give an example, if a woman has a mitochondrial disorder, all of her children will inherit the condition, but only daughters will be able to pass on the condition to their children.
This characteristic pattern has an important application in tracing material lines and in the understanding of inheritance of particular metabolic disease.
It is necessary to know that these mitochondrial diseases can vary greatly in their severity and their symptoms, primarily depending on the number of mitochondria affected and the specific mutation.
More often than not, these diseases generally affect the high energy requiring organs and tissues, including the muscles and the nervous system.
In summary, X-linked inheritance involves genes on the X chromosome and can lead to different patterns of inheritance in males and females, depending on the dominance or recessive nature of the trait.
Mitochondrial inheritance, on the other hand, involves genes in the mitochondria and to only pass down exclusively through the maternal line.
When genetic diseases are known to have these patterns of inheritance, they can be well studied for treatment and diagnosis strategies and proper counseling of such risk groups and their plans for progeny.
I thank you for listening to our presentation. We hope this has helped clarify the difference between X-linked and mitochondrial inheritance and their significance in genetics.